Good afternoon, my name is Michal Uchmanowicz and I'm recording my CST 452 senior project presentation. Alright, now within my senior project I have created three things. I have created a game that both a human and an AI can play. The game is pretty simple and I'll get further into that in a moment. I have created a demo where the AI plays the game through an implementation of a genetic learning algorithm called NEAT. Now, NEAT stands for Neuroevolution of Augmenting Topologies. It's based around the idea of evolution within machine learning, kind of like Darwin's evolution. And then finally, actually really quickly, that demo will post data models to a MySQL database located within AWS RDS. And then finally, I have a Django web app. Now, this will pull the information from a MySQL database located in AWS RDS, and it will display it in a neat manner within a graph as well, and it'll give you some information about the game and about the AI itself. And that's hosted within AWS ECS. So both the both the website, the Django website, and the database are hosted within AWS. But let's get into the game. So the game's pretty simple. Let me go ahead and turn one thing off. And I'll show you why I turned this on or off to begin with. When we play the game, it's a pretty simple game. We are given one output. We can swim up by pressing space. That's it. Otherwise, we'll be pulled down. And this is just to force interaction with the game so that a player can't, provide no input or no output and still get a good score. But within the game, you're tasked with going as far as you can while obtaining worms, and then these worms give you points. Going as far as you can gives you points. You get points just for being alive, and you actually get points for passing sharks and not colliding with them as well. So, if you collide with a shark, the game ends. If you fall off screen, the game ends. If you hit the fisherman or his hook in his boat, then the game ends. So realistically, all you have to do is stay alive and gather worms, okay? So it's a pretty simple game. Now we throw an AI into it. So we use NEAT to create a population of AIs based on a configuration file. So that configuration file looks like this. So here we specify that we want 25 AIs. We want them to use the activation function of tanh. We want them each to have a connection, the probability to add a connection between nodes, half. We can specify things like inputs, number of hidden inputs, number of outputs. We can specify the initial average weight that a connection has, right? Things like that. So how does a NEAT AI work? Well, like standard AIs, it has an input layer and hidden layer and an output layer. However, each one of these nodes within each layer has its own weight and bias, and then it can be connected to other nodes within the same layer, other nodes outside that layer, and those connections have their own weights and their own probabilities to be connected as well. But essentially, we create a population of 50 AIs and we throw them into the game. Now, what do the AIs know about this game? Well, we're passing each AI the distances to objects. We're using kind of like a radar, specifically a ray casting algorithm. So let me go ahead. This is what the demo looks like. But if I remove the background, which is what I had before, then we can show you, what the game actually looks like to the AI. So each AI will be given 20 different inputs. Now, 19 of these inputs are these lines that you see here on the screen. Now, of course, you don't see it for each AI just because it'd tear apart the screen in my computer and it would look awful. But you get the idea. It's just given to one so that we can understand. But each fish is given about 20 of these lines that it shoots out from the center of the fish. Now, if this line intersects with any kind of object, like a fish or a fisherman, then the distance to that intersection will be given to that fish. So these fish always have 19 distances being given to them, as well as the y distance to worm. So the worm we didn't actually use we didn't use ray casting for the worm, we just gave it a y distance to worm. And we just used the ray casting for enemies and obstacles. But essentially, fish shoots out a line. If the line intersects, it's given the distance of that line. Okay? And that's how the AI decides whether to output or not. So let me further explain. We take these 50 AIs, we throw them into the game, and then whichever do best out of these 50 AIs, we save the top 2, and then we say, hey, let's breed these 2 together, let's cross them and create a new generation with similar traits to the parents, similar traits and characteristics. Now, these traits and characteristics are these connections, these weights, these biases that the topology is composed of, right? So with each generation, we just create one that's hopefully better than the previous one, and then mutate it a little bit based on how it did last time and see what happens. So essentially, we're kind of running one little random number generator every single time, just slightly adjusting values until we get something that works, right? That's the best way to kind of explain it. And we do that with each generation, of course. So we're at generation 9, right? And we already have a fish that seems to know what he's doing. He just went between the 2 sharks. He went above these 2. Unfortunately, he didn't go under those. But sometimes we have an AI within, the first 10 generations that's really satisfactory. Other times it can be 100 or 200 or 300. And that's simply based on evolution, right? With Darwin's evolution, I mean, you can mutate both negatively and positively, right? But anyways, let me show you what happened after about 300, 400 generations overnight. This is here what we've got, a trained model. Now, how do we determine this trained model? Well, we tell the neat algorithm, hey, if you find any fish that exceeds a score of over 15,000 within the game, save that fish into a file. I want to use it later. And so that's essentially what we've did. We ran a fish overnight for about 300-400 generations, and then we saved it once we got something that was satisfactory. And you can see that it's doing really well. I mean, it is doing really well for being given just basic distances to objects, right? So that's how the AI works. So we have successfully trained it in playing this game that I've created. Main point of the project, done. But another secondary point of the project was to show this information within the Django web app. So within that last demo we ran, we ran about 11 generations. And so let me pull up the Django web app and show you that this has all been retrieved from a MySQL database. And you can see it goes up to 10 generations and then shows a generation 3272. Now the generation 3272, that's the only issue I have with this project. Each time we run the simulation, it posts another generation by mistake. So realistically, I've run the simulation around 3,272 times since I first started. So it took a while to get it to work. And I was having issues because I was originally trying basic distances to objects, and it took me a while to figure out how to use the ray casting algorithm correctly and have those distances returned. But essentially, you've got these 10 generations, and it didn't post the 11th generation because we were currently running the 11th generation when I stopped it. But you can see that all that information has been posted to a MySQL database and then retrieved down to this Django web app. Now with this information, we can of course, look through it. We can look at the graph. We can also sort it. So, generation ascending right now. What if we go generation descending? Oh, well, what if we want to know which generation had the best fitness without looking at it too hard? Okay, well then we just sort it by best fitness and look all the way at the right. Generation 9 with 1377. That's the basic premise of the web app. Now the web app also provides some basic information about what my project is, about the game, and about Neat and how it was used in this project. And then of course we get the demo info, which is the sort and the list and the chart. We can also log in. So if I register, if I go in Mike Uchmanowicz, mike@gmail.com, username Mike Uchman, password, and we register. And we should see that account created, welcome Mike Uchman. So if we go ahead, we can go ahead and then log in Mike Uchman, password, and that gets us logged in. So that would be the end of my project. Thank you for watching. Take care.